Hello, so welcome to DVClub. This is the third DVClub we've held in India, the second one at Cadence. DVClub is a worldwide phenomenon. It was started in Austin, but it now has chapters all around the world. There's some information there regarding access to DVClub and the events we organise. And that's a one-day verification conference that we hold in Europe. Today's talk, we're slightly behind schedule, but I think we can catch up. It's all about UVM and the adoption of UVM. We have two speakers here based in Cadence in Bangalore, and a number of people online as well. Our first speaker, I'm going to hand over to him now, is Vinod. He's from Texas Instruments in Bangalore. He's going to speak for half an hour on his presentation before he hands over to me. So I'll just bring up his presentation now. Whilst I'm doing this, if you have any questions, feel free to ask them. You can either ask, is everybody on mute, Sarah?
Everybody is on mute. If you do have a question, if you can enter it into the question section of the webinar panel that you see, then we'll do them at the end of the presentations.
Okay. And if you do have any questions as well, at the end of the presentation, we can take people off mute to hear those questions, can we?
Yes, we can.
Hi, good evening everyone. This is Vinod from Texas Instruments. Today I'll be presenting something on the system Verilog UVM reviews. Basically, this is something I have presented. This is something which I worked on last year. So I actually presented this in Cadence Live user conference. So the topic is reusing the system Verilog UVM-based IP verification environment at the system level. So I'll be discussing about the challenges that we face and basically the solutions that I am proposing. So this is the outline of the presentation. First thing is the introduction and the problem, then the methodology that I'm proposing, then analysis of the results. So to begin with, so people who are working on system level verification, right? The SOC design verification involves checking the integration between different modules as well as simulating some use case scenarios. The first part is pretty straightforward. Basically, you can have some sort of checkers to integrate the connectivity between different modules. But then the second one, which is simulating some use case scenarios, this requires some test bench or some driver or a BFM, which is the first functional model inside your test bench. So if you have a system on chip, typically you'll have tens of such modules. So developing such a TV model per module is not easy. So one of the earlier approaches is to use the IP verification environment at the system level. So this is something which was already done. But now these days, with the popularity of system Verilog, UVM is really becoming a popular environment for verifying standalone modules. So, but then there is really no proper guideline defined to reuse the UVM-based IP environment at system level. So basically, to give a history of the problem, right? So I was working on some system which is okay. Sorry. So basically, I was working on a system. It was a microcontroller. Basically, it was Cortex-based microcontroller for which we were using. We were designing certain custom peripherals as well as we were using some standard peripherals. So while we were designing some custom peripherals, they were designed from scratch. So we had to have verification, doing standalone verification for that module. So we we opted for system Verilog based UVM to verify the a module at a standalone. So we did the random verification using system Verilog, and then we had to close the coverage on that. We achieved once we achieved the 100% code coverage, we had to integrate it at the system level. So at the system level, the challenges are different. So at system level, we had to simulate some of the use case scenarios there. So at that level, I was again looking for some BFM or some Verilog model, so that I can simulate those cases at my bench. But then because it was a custom interface, I didn't find any. So I had to again either had to develop something again from scratch, or I have a challenge of reusing my bench which I had developed for standalone bench. So so that's when I started this work. So basically this work is aimed at addressing this problem, where since there is no real proper guideline defined, I searched on the net, and I couldn't find anything there. So that's when I kind of choose to try reusing my environment. Then I faced some challenges there. So what are the solutions I've opted for that I'm presenting? So as I said, I'll be presenting the challenges and the solutions in designing the SOC reusable UVM environment. So here I have highlighted the major challenges that will come in when you try to reuse the UVM bench. The first thing is connecting the IP verification environment at the system level. Then the next one is synchronizing the IP environment operations with the operation of a CPU or a mask hub at the edge system level. So here there is no virtual sequencer. Basically you will have a single sequencer. So you need to synchronize the operations between your CPU, which could be a Cortex based or a DMA, and your sequencer. So that is the second challenge. The third one is simulating these tests or use case scenarios at the system level using the IP environment. So I kept one slide just to give an introduction of people who are relatively new to system Verilog UVM. So system Verilog is it's a hardware design specification and verification language. It's like an extension of Verilog with object-oriented programming. So all these simulators support this system Verilog, so you don't need any additional overhead on the simulator. And then universal UVM is basically the universal verification methodology. It's an open source verification methodology based on a library of classes. So these classes are again they borrow the concept of object orientation, OOP programming. So they are all dynamic in nature, so they'll be created during runtime. It uses an architecture for building the verification environment that enhances reusability. So that's the beauty of UVM. The architecture is so well defined that it enhances the reuse, and it uses TLM interfaces for connecting the verification blocks. Then it provides features using which objects in the ENV can be modified during the runtime. So this is the object-oriented programming. So I kept one a picture where how the IP environment looks like with when you try to use UVM. So you have a design test. So let's consider this as a standalone module. So the module will have an IP interface, and then it will have one system interface. When I say IP interface, let's take an example of some say UART, universal asynchronous receive transmitter. So if you take a UART, simple UART, it will have two interfaces. It's the programming interface where you should be configuring its registers and you can access the FIFOs there. And then the other side you'll have the basic UART protocol, which is the TXRX pins coming out. So typically you'll have two agents there. One agent is it takes care of the UART interface, which I call it as IP interface agent, and then you'll have one system interface agent. So under UVM, you'll have basically under agent you will have some driver and a monitor. So driver is something which will be driving the interface stimulus into the design through the interface. Monitor is something which will be monitoring the traffic that is coming in, and basically you'll have a sequencer which will be taking the sequence from the virtual sequencer, and it will be routing it to the driver using the TLM interface. So here there is this virtual sequencer which basically has virtual handles to these different sequencers. So basically your test case will be a virtual sequence which will be a combination of multiple sequences. So this is the typical environment, verification environment using system Verilog UVM. So this is again just an explanation of what I've just talked about. So your test sequence will contain a mix of IP interface sequences and system interface. Virtual sequencer will channel the sequences to their respective sequencers. Sequencer will execute the sequence and pass the stimulus to the driver through the TLM port. And driver will drive the stimulus through the respective. And monitor will be monitoring the incoming data. Now let's get to the problem. So how to make the environment reusable at SOC. So the issues and the solution I'm proposing. So the first issue is not all the components in the environment are required for the SOC. As I said, if you take the case of UART, if you are trying to integrate the UART at the system level, then basically your programming interface will be replaced by a master like Cortex, or some processor or ADMA. So the whole agent that you have kept at the IP environment for taking care of that need not be used. So for that, basically you can pass on a parameter that controls. So here I'm UVM. I'm actually referring to some configuration attribute which will block the build of components inside the environment, and keeping the condition always true will ensure no effect on IP verification. The second one is simulating a complex scenario at a system level requires a communication between the CPU and the sequencer. So as I said, the system level, one of the agents will be replaced by the actual design. So there is no concept of virtual sequencer handling multiple sequencers. You'll have only one sequencer and the CPU. So basically there is no handshaking mechanism between the CPU and the sequencer. So for that, what I did was I defined a set of triggers in the IP interface. So I call it as triggers. Basically, I left them unconnected in the IP verification. And the other thing is I defined a handle to the interface in the virtual sequencer. So I don't know whether how it goes with the methodology, but this is something that serves the purpose for me. So I basically defined a interface in the virtual sequence. Since this is a virtual interface, unless I assign actual interface to that, it will not be, it will never be assigned. So at the IP level, I will not be calling this task. So this interface will not be assigned at IP level, but system level I will be. So coming to the next thing, the SOC pins will be different. So this is something really straightforward. So I just create a Verilog wrapper around the environment. Use this wrapper to map the IP interface to the SOC pins. So the other thing is the CPU or ADMA will replace the system interface agent. So as I said, you can disable the you can pass the argument to get the build during the build phase. You can disable the other agent, or in fact you can actually you can do multiple things there. You can actually connect the interface to its inactive value so that the driver or the monitor will not be even triggered. So finally, there should be a proper communication between the CPU and the IP sequencer. So remember, I defined a set of triggers in the interface, right? So I'll be first assigning the virtual interface to the sequencer through this task call from my test sequence, and then I'll be connecting the control triggers which I defined in the interface to general purpose IOs of the SOC interface. So usually in system on chip, right, you'll have certain IOs coming, bidirectional IOs coming in. So I'll be connecting these two control triggers to the general purpose IOs, and let the CPU and the sequencer control one trigger each and monitor the other. So I'll explain, I'll show you how when I say control one and monitor the other. So I have a sample code that I took it from my bench. So synchronize the operation of the CPU and the IP sequencer through the trigger control. So I'll show you in detail how what I meant by the synchronization. Then include the trigger control only in the test sequence and retain all the IP sequences. So the test sequence will be the only difference between the IP and the system on chip. So so what I meant here is I'll be retaining all the IP sequences that I've coded for my IP interface agent. So all the sequences that are required for the programming of the IP through the programming or the whatever I drive through the interface, the specific sequences I'll be retaining. The only thing is I'll not be calling the other sequences, which are, for example, the CPU, which is a APB or HP interface sequences, which I'll not be even calling. So actually the test sequence is not really a virtual sequence. It's more like a the IP sequencer itself. So it's only a one-to-one connection between my test sequencer to the IP sequencer, and I'll be calling only the IP sequences. I'll not be calling any test sequences. So this is the schematic of the proposal. So as I said, the IP interface agent will stay like that, but my system interface will be replaced by a CPU or the DME. So the whole thing which I showed before, right? The whole system interface agent will not be coming into picture here, and my virtual sequencer is like my test sequence is more like my IP interface sequencer. So it will be virtually running only on one sequencer. So these are the set of triggers that I was talking about, control triggers. As I said, I defined this in, so basically I defined the interface in the virtual sequencer. So as I said, I'm not sure whether it's the correct thing to do, but this is something to solve the purpose for me. For example, test sequence at the system level. So yep. So this is the test sequence that I was talking about. So this is the function. So this is the function tab which will be assigning the virtual interface the sequence. So first I'll be assigning that, and then I'll be waiting for I'll be waiting for a trigger here. So when I say p sequencer.ip sequencer interface.stop trigger, this is basically, this refers to the stop trigger that I have connected to the GPIO pins in my system. So when my system comes up, basically the test sequence will be executed automatically to the run task call, but then it will wait for the trigger to come in. So till then it will not be generating any stimulus on the interface. So the CPU or the Cortex basically boots up, and when it tries to execute when it is executing the test case, once it is done with all the configurations, it will send a trigger. So after that, basically wait for this wait statement will get over and will move on to the next set of sequences, which will basically drive the stimulus into the interface. So what I was explaining is this is the test sequence that I have captured from my code. So as I explained before, I'll have a virtual interface connected in my virtual sequencer, and since it is a virtual interface, I need to assign it to the actual interface that I'm doing through the task call. This task is the connect interface task that I've defined. So this is the connect interface task. So where I'm actually assigning the actual interface to the virtual interface. So I'm calling this at the beginning of my sequence. So there is a connection established between the virtual sequencer and the actual interface. And then once my system comes up at the once my CPU boots up, it will start executing the test case. So, but on the other side, the UVM is, the run task is called at the beginning itself. So the UVM starts to execute its sequence, but then it sees the wait statement here. So here I'm simply waiting for the trigger to come from the system, which will be generated by a CPU right into the GPIO. So till that point, my test sequences, which is the IP sequences, UVM will not be executed. So once my Cortex boots, or once my whatever the master boots are, once it starts to execute the test case, it does all the configurations that are required, and then when it requires the stimulus to be generated from the external master, it sends a trigger here. So that's when the wait statement, actually the sequencer comes out of the wait statements, and then it tries to execute the sequences that you have kept. So this is how I'm synchronizing the operation between my virtual sequencer here and the Cortex or the master at my system level. So basically, once my sequences are done here, I'll have a global stop request. In UVM, you'll have that. So it depends on the environment verification environment that you're using. You should be waiting for both your Verilog as well as C code to say with case of C code, we run with C code. As you said, we load the code into our internal RAMs or flash, whatever. So basically, it depends on the environment how it stops the simulation. So it should be waiting for both system Verilog UVM and as well as the C code to finish its execution, and then finally it should wait for both the triggers, and then it can give $finish later. So this is a snippet of my code. So basically, using these wait statements, I'll be synchronizing the operations. Yeah, but then what event you should be again? There has to be physical connection between your system or so. Then the analysis part. So basically, as I said, I have implemented this on a custom peripheral which has AHP interface that is used for programming or configuration as well as data path, and then a slave interface which is basically a custom protocol that we had. So first, I in fact to begin with, right, I did not have the. I was not having this in the background, so I coded it for the sole purpose of doing it IP verification. Then when I came across this thing, right, so I started updating the IP verification environment. And as I said, it's only the test sequences that differ, so I need not be updating anything in my IP suite. I just need to update the test sequences. So these test sequences which I have kept here, right, this will not be used at the IP level. There's only a single file that I have coded specifically for system level. And these IP4 sequences, right, so these are the ones which I'll be calling from my IP bench. And as I said, the sequencer environment, everything I've used it from IP environment, and I need not do anything special at the IP to. So it's only the test sequences that differ. You just need to code the new test sequences as well as the C code or basically whatever the software that you need to develop. And I'm able to run these different scenarios at SOC using this environment. So it is, because of the UVM, it is really flexible for me. And I could generate some random stimulus using the UVM. So it was really, I could really simulate some complex cases, which I would say would not have been possible with, say, a bus functional model or some other Verilog test bench. So the effort spent on making the environment reusable, as I said, you hardly need to do any changes to the IP environment. Just need to change the interface and define some certain tasks. So I would say it is less than total 2% of the total environment, total development effort. So as conclusion, I would say any environment supported to the SOC with minimal effort. But the limitation for this is if you're trying to use the same Verilog, same test bench for FPGA or Palladium boards, basically which we do at TI, right? So you'll have a common test bench which will be used for DV simulations as well as some validation testing. In that case, we basically cannot use this. So maybe that's what I kept it as scope for further work. So to conclude, right, I would say the idea is really simple here, but it is really effective. The effort you need to spend is really simple, and the idea is also simple. So that's all I have. If you have any questions. No, scoreboard I used it at IP level, but then here I do not have a scoreboard. So since it is at system level, right? I'll not be really using some random stimulus. Maybe some directed, mostly it is directed testing. It's DV's top level, right? Be directed testing. So I'll have bit of randomness in the stimulus, but then scoreboard is more at the C part where I'm sending some data and that data I'm exporting through the other channel. So it's more like a C-based test. It is hard-coded, so it's not a hard. Not the test cases, yes. Yeah, the actual sequences, right? When you go to the lower level of sequences. So those will
Vinod, can I interrupt a moment? My apologies, Vinod. Can I ask you to repeat the question for the purposes of the webinar, please? Because we can't hear the questions as they're being spoken in front of you. Thank you.
The question is whether I use any of the IP test sequences to the system level. So the answer is I didn't use the test sequences. I use the IP sequences because the test sequences are more like use cases. So I cannot use the virtual sequences from IP level to system level. What stops me to reuse it at Palladium? Basically, I think it's more like a constraint on UVM. When I had this question when I started on UVM. So, can this be synthesizable? The UVM, the answer was no. So that's why I kept it as a limitation. So the whole UVM sequences. Yeah. Any other questions?
We have one question. Excuse me. We have one question from the webinar. I will just repeat the question for everybody. I'm having FIFO environment in UVM. Which module do I need to call the global stop request?
It depends on your scenario, right? No, I didn't get your question. You have a FIFO model?
No problem. Bear with me. I'll just unmute that. Hello, I've just unmuted the originator of the question. Would you like to repeat your question and ask Vinod? I'm going to mute him again. It sounds like he may not have audio. What he's just saying is whether I will call in base, test or top is what he's asking, if that makes any sense to you.
The base test. Okay, I'm not clear on the question.
Okay, what I'll try and do is I'll try and unmute. It's obvious he's listening. I'll try and unmute Masilamani, and hopefully he'll be able to answer the question himself.
Just drop the question, Sarah. Let's just drop that question. I think we have one more question in the room.
Yeah, we have one more question. How much extra time is going to take to compile and use UVM libraries?
Sorry, you're talking about the simulation time?
Unknown. It's a written question, so I don't have any additional information. It just says how much extra time is going to how much extra time is going to take to compile.
At all because no, it's not. I mean, I've never really felt that it's an overhead. So basically, we have I don't know, the UVM library is not so big, right? So because based on if you try to compare the compile time of our design, then it is really negligible. So depends on how big your design is, and based on our designs, it's never an overhead. I never felt it is big.
Thank you. We have no further questions.
How different is UVM to OVM? Is that? I think it's more a question.
Apologies, we seem to have lost audio again.
Yep. Oh, basically you'll be using that. So, so if you have any constraint, right, that is applicable to the design. So, I mean, there is no way. It's like, for example, take a case of any standard peripheral node. Let's take a case of UART where actually the payload could be only this. So that is applicable to the system level also. So it's I don't see any constraints. So all the constraints you can. Yeah. Thanks.
Thank you, Vinod.